It's our pleasure to introduce Dr. Chris Henry, who's going to give us a presentation on lithium deposits in Nevada. Chris got his bachelor's in geology at Caltech, and then got his master's and PhD at UT Austin. And he stayed in Austin and worked at the Texas Bureau of Economic Geology until he moved to the University of Nevada, Reno, and the Nevada Bureau of Mines and Geology in 1993. And I guess the university and the Bureau work together closely, which is an advantage for your students. So he likes to address basic and applied geological problems, primarily through geologic mapping, supplemented by 4039 argon dating and some uranium-led geochronology, along with geochemistry, structural analysis, and whatever else he can bring in to apply. He officially retired in 2019, but continues to do geology because he enjoys it, and we're very grateful that he's willing to share his expertise with us today. So thank you, Chris, for taking time and doing this.
Well, thank you. And yes, geology is fun, so I continue to do it. This talk is going to focus on the lithium clay deposits of Nevada, particularly in the McDermott caldera. But I'll start with a little bit of background. I assume everybody here knows the importance of lithium for lithium-ion batteries, electric vehicles, and such. A lot of research being done on battery technology that I try to keep up on, but it's way out of my expertise. There's a lot of talk about, for example, solid state batteries, but all of them would use lithium also. So it just looks like lithium, by being the lightest metal and having a high energy density and many other good electrical properties, is going to continue to be have increasing demand. And currently, lithium is mined. The two leading countries producing lithium are Australia, which produces from pegmatite. It's the, and I hope you can see my pointer here, it's this light colored material here in this open pit in southwestern Australia. The pegmatite has spodumene, a lithium pyroxene, amazingly enough, this composition, and that's what they're mining. They initially started mining for tin, but now they're mining for lithium. And this photo on the right here is just a interesting little thing. This is a pegmatite in Maine. This thing here is a giant spodumene crystal. And so in some pegmatites, they can get really big. Now that's the major mining of lithium, but lithium is also produced from brines, particularly in the Andes of South America. Brine, extremely saline groundwater, much more saline than seawater, and commonly very enriched in lithium. And in a brine operation, they pump the brine to the surface into these individual lined ponds, where it evaporates and is chemically processed to wind up with lithium carbonate. The only lithium producing operation in the United States is in Nevada, a small brine operation, much smaller than any of the Andes stuff, in a place called Clayton Valley. And this is just a photo of the brine operation there and its evaporation processing ponds. China is the third leading mining country for lithium, but more importantly, it is by far the leading processor. The spodumene from Australia is shipped to China for processing, where it's ultimately turned into lithium carbonate and lithium batteries, and China is by far the biggest producer of them. And this is a concern for the United States and a lot of countries. So everybody's looking for their own sources of lithium and potentially processing too, to generate their own batteries. And Nevada has a whole bunch of lithium clay deposits. Now, this is a very newly recognized type of mineral deposit, first recognized in the mid to late 70s. And at the time, there wasn't a great demand for lithium. So There just wasn't a lot of study, and what study was done was published in mostly a bunch of gray literature, which had some deficiencies that we'll address a little bit as we go along. And this map on the right here shows really just the major lithium prospects in Nevada. There's a lot more, but in some cases with very little information. So this just shows the ones that are the major ones with significant information. The lithium brine deposit is down in here, just to the right east of Rhyolite Ridge, which is a lithium clay deposit, but one that's enriched in both lithium and boron. That's one of the ones I'm going to really emphasize in this talk. The others, really, the main one is going to be the McDermott caldera, particularly Thacker Pass here. Additionally, Rhyolite Ridge, lithium boron, Tonopah, where there's a cluster of lithium clay deposits, and then way out here in the northeastern part of Nevada, Nevada North. And note the Tesla Panasonic Gigafactory here just east of Reno. This is a joint venture essentially between the two, making lithium batteries and making batteries for both electric vehicles and for sort of fixed storage. Interesting thing about the Tesla Panasonic Gigafactory is that they import almost all of their lithium from China. And so that's a situation we want to deal with. Lithium exploration has been very good for geologists in Nevada. Nevada's a big mining state, particularly for gold, silver, copper, and employs a lot of geologists for exploration. That's equally true for lithium. It's employed a lot of exploration geologists, but then there's a lot of other things involved too. Mining, for example, involves a lot of geotechnical engineering, environmental studies, both done commonly by geologists. And then just mineralogy alone is important because that's a big factor in processing. Okay, so mineral exploration in general and lithium in particular, good for geologists and good for Nevada employment. Okay, I am going to talk about what I call the big four: McDermott caldera, Rhyolite Ridge, the lithium boron deposit, Tonopah, and Nevada North. And because these are new deposits, there's not a long term of detailed studies and fully understanding the deposits. There's been a lot of recent activity because of the increase in interest, and a lot of recent publications, but the deposits are not really fully understood. Some things have gotten pretty clear, nevertheless. All of them are formed in closed basins. McDermott is a caldera closed basin. I'll say more about how that works in a minute. All the others are structural tectonic extensional basins. All of these closed basins have rhyolitic tufaceous sedimentary sequences. All of those sedimentary sequences have undergone what's called closed hydrologic system diagenesis, and you'll see this abbreviation throughout the talk, and I'll explain what that is. All of them have lithium smectite. Smectite's a montmorillonite type clay, and all these deposits have lithium smectite. Two of the deposits, Thacker Pass here, the McDermott caldera, and Nevada North over here, also have lithium illite, which is a higher, it's also lithium clay, but it has a higher lithium content, and it's sort of advantageous for a lot of processing. And so having the lithium illite is a benefit for these deposits. Now, one of the big questions remaining about the lithium deposits is the origin of the lithium illite. I think at this point, most geologists accept the idea that diagenesis, this closed hydrologic system diagenesis, has played a major factor in generating the lithium deposits. But the origin of the lithium illite is a little more contentious. One view has been published that it's a hydrothermal that is the illite forming at more than 200 degrees C. That is not my view, but it's uncertain. And certainly all of our big four have the potential for a hydrothermal contribution. McDermott caldera, for example, the magmatism associated with the caldera could drive hydrothermal solution. And these other spots all have, at least to the extent we know, have some concurrent rhyolite magmatism. Nevada North, we really know very little about. And I will make the point that just basic geology has been critical in understanding these deposits. And because we don't know much about the basic geology in Nevada North, our understanding of it is a lot less than any of these others. I'll briefly mention, just the question of, is there a special rhyolite composition that is good for lithium deposits? That's an open question, but there's some suggestions that that's true. And I'll even talk a little bit about published misinformation. Okay, here's a Google Earth image of the McDermott caldera looking north. It's on the Nevada-Oregon border, which you can see along through here. The McDermott caldera is an early part of the Yellowstone hotspot. And, as the North American continent migrated over the hotspot, magmatism migrated to the northeast, and it's now in the Yellowstone area over here. And this, the McDermott caldera is really pretty well preserved and pretty well exposed. And you can see this light, dark boundary up here. That's the structural margin, northern structural margin of the caldera. Comes down here, shifts over here, comes down like this through Thacker Pass, which is a big deposit, and then out like this. Now, calderas. I think a lot of you know about calderas, but maybe some of you don't. So I'll just quickly outline what's going on there. This figure on the right is a classic one by Peter Lippmann from 1984, discussing formation of calderas. And basically the concept is there's a big magma chamber down here. Now, Peter showed this as a bunch of individual apophyses, and I think more likely is on the left here is a sort of a large coherent magma chamber, but both of these are diagrammatic. In any case, what happens is the magma starts to erupt very explosively. A lot of rhyolitic magma erupts as pyroclastic, a Plinian eruption column or boiling over that generates pyroclastic flows. Because so much magma erupts, the ground above the magma chamber becomes unsupported, and it collapses down to fill the gap left by the erupting magma. The crust just can't hold up a giant cavern like that. And so you get this collapse as shown in Peter's diagram here. It's got major faults along here, and this block, which was up here before, is now subsided. That generates this large basin. Caldera is just Spanish for cooking pot, and that's basically what it is. It's a large closed basin. Because the ash flow eruption and collapse are going on at the same time, a lot of the pyroclastic material ponds within the caldera, as shown here. You get a very thick intercaldera section that can be many kilometers thick, and it generates a closed basin. We're just seeing a cross section here, but this rim would go all the way around, and that would be a closed basin, which in general is almost immediately occupied by a lake. Crater Lake in the Oregon Cascades is a good example of such a thing, as a fairly small example, and these are much larger. And that lake starts to accumulate sediments being washed in from the caldera margin, or pyroclastic material from adjacent eruptions filling in. And you get a pretty substantial intracaldera sedimentary sequence, and that's really important for our lithium mineralization, as we'll see. And a final stage of caldera development that's common but not ubiquitous is that the underlying magma chamber continues to rise, and it domes up the overlying subsided caldera block. And so here's our intracaldera tuff that initially would be down and be covered by younger deposits. It's pushed up into a topographic structural dome that's exposed in the middle of the caldera. And indeed, we see exactly that for the McDermott caldera. Again, here's our ring fracture system coming down along through here, through Thacker Pass. And incidentally, Thacker Pass is our major lithium deposit, lithium illite deposit in particular. The lithium clays are very soft. They don't crop out well. The stuff up to the north, the light colored material here in the north, is sort of best exposed, but even that's very poorly exposed. In Thacker Pass, it's largely covered by quaternary windblown sand and fluvial sediments, and just the lithium clays are not well exposed at all, but they've been extensively drilled into. Anyway, so our caldera here, this area here, the dark area that going up through the north through the middle of the caldera is the resurgent dome. And this photo on the right, lower right, is looking northwest at that resurgent dome across Thacker Pass, which is in here. And this is sort of the typical non-outcrop of the lithium clay deposits. You can see a little bit of drilling work up here that's related to the lithium mining activity. And then this area here is the uplifted intracaldera tuff, which we wouldn't see within the caldera without the resurgence that this represents. This view on the upper right is looking here at the western edge of the caldera. The caldera margin comes through about like this, but it's been cut off by a basin range fault that dropped down the valley off here to the west. And so we get an actual cross-sectional view through the caldera system. And this here is part of the caldera. You can see what's exposed is more than 400 meters thick. This is all intracaldera tuff. This band through here and this through here are actual layers in the intracaldera tuff, which has undergone a somewhat unusual but interesting process of secondary flow. The ash flow, initially it's a pyroclastic eruption, pyroclastic flows, they pond within the caldera, but at some point they consolidate, become more solid rock, they're still hot and somewhat ductile, and the intracaldera McDermott tuff actually flowed, probably flowing off the caldera wall, and it made these giant folds. This is part of an anticline in the McDermott tuff through here, and that's an unusual aspect of the McDermott tuff and caldera, and one that fascinates a lot of people. Okay. And there we go. This is just a ground view of the lithium mining operations, which are under construction. In the background here is the actual lithium deposit. And because it's such soft material, they don't have to do any blasting. They just go in with big shovels and dig the stuff out. These buildings in the foreground are part of the lithium processing, where they'll actually process the lithium clay to make lithium carbonate. And that area is now right in here, just above the Thacker Pass label.
Oh, okay. Were you looking at the aerial photo?
Okay, a little bit about the evolution of the McDermott caldera. Its middle Miocene igneous activity this time started with eruption of the Steens basalt, which is a part of the Columbia River basalt group, and all this magmatism is part of the Columbia River basalt hotspot. With time, the eruptions became progressively more silicic, and we got a variety of both peralkaline and metaluminous biotite rhyolites. And this culminated at 16.39 million years with eruption of 1,000 cubic kilometers of McDermott tuff and caldera collapse. And I'm going to talk a lot about some precise dates as I go along here. And these are based entirely on very precise argon 4039 dating and a lot of stuff that are going into making up these numbers. And so in 1639, the tuff erupted, caldera collapsed. A lot of the tuff ponded within the caldera, and some of it flowed out outside of the caldera. And so, for example, here on this map on the left at the southern end, we can see a little bit of outflow McDermott tuff capping pre-caldera rocks in the southern caldera wall. Okay, immediately after collapse, we generated a caldera lake, and that filled with a lot of rhyolitic tuffaceous sediments, the TIS. Oh, and I should have pointed out this TMT, this thing through here, this is the McDermott tuff intracaldera exposed in the resurgent dome. This TIS through here, and then very poorly exposed through here, but underlying all this yellow quaternary material and throughout the eastern part of the caldera. That's the intracaldera sediment that filled in the caldera. And this rhyolitic material mostly came from not from the McDermott caldera itself. There's some continued explosive activity there that did contribute, but a lot of it came from other calderas in the vicinity and other rhyolitic eruptions. And we know that because of their age, their mineralogic and chemical composition of the actual tuffaceous deposits. Resurgence occurred pretty soon after caldera collapse. We can constrain it between the time of collapse and about 16.1 million years, and most likely pretty close to 16.31, but definitely no younger than 16.1 million years. And that was related to post-collapse volcanism. The magma chamber continued to rise and domed up the McDermott tuff into the resurgent dome through here. Caldera magmatism completely stopped at 16.1 million years. There was no caldera-related activity after that. There were, however, some basalts, particularly down in the south part of the caldera, but a little bit up in the north also, that are unrelated to the caldera system. They are low potassium olivine foliites. That's what this abbreviation is here. And they're between about 16.0 and 15.7 million years. Okay, as soon as the rhyolitic tuffaceous sediments started to accumulate in this lake and be deposited, they started to undergo this closed hydrologic system diagenesis. And what is that? Well, volcanic rhyolitic glass is actually very unstable. It easily dissolves just in regular groundwater. And as it dissolves, all the constituents of the glass go into solution. So that's a lot of silica, aluminum, sodium, potassium, etc. And that drives the fluid that is interacting with the glass to become more saline, increases the pH, so it becomes more alkaline. And because this is a closed basin, that is, creeks may be flowing off the caldera wall into the caldera basin, but the only outlet for water is through evaporation. There's no rivers or streams draining out of the caldera. And evaporation, of course, just increases the salinity, the total dissolved solids of the fluid as it goes along. So the combination of solution of glass and evaporation, you get extremely saline and alkaline systems. And a series of minerals, and this has been well documented in the literature going back 50, 60 years, a series of minerals and other things precipitate, starting most notably, a lot of silica, you get opal, but then you get smectite, the lithium smectite in this case, a variety of zeolites, and a bunch of other minerals, and I'll say a bit more about those in a second. The lithium clay deposits are entirely in these intracaldera sediments. The entire section is mineralized with the lithium smectite. So mineralization process, starting with the closed hydrologic system diagenesis, must have continued to at least to 15.7 million years. And the reason we know that is we've got extensive dating of the tufaceous sediments. There's individual points here from outcrop, and then there's sections here from drill holes, the north and south. And the dating, the youngest material, the oldest material is just barely younger than the McDermott tuff itself. The youngest is around 15.7 million years, but there's some recent things that suggest there may be some even more younger deposits, and I'll say something more about that in a second. Anyway, so the entire section is mineralized, so the mineralization process continued to 15.7 million years. Now, I mentioned that this was the lithium mineralization and the diagenesis were recognized a long time ago, really in the mid to late 70s. And a particular guy, Jim Ratuba with the U.S. Geological Survey, did a lot of this work and unfortunately published it mostly as open file reports that were not reviewed and don't include much data. So it's been a bit of a drawback. He didn't use the term closed hydrologic system diagenesis, but he certainly recognized it in that he recognized extensive minerals developed in that diagenesis. And this explanation here, you start off with glass and clinotillite, aragonite. Those are zeolites. Those are very common products of the diagenesis. Potassium feldspar, this is orthogenic potassium feldspar produced by the diagenesis. It mentions analcime, that's another zeolite. We also have found albite, the sodium plagioclase form, that's a diagenetic mineral, commonly replacing analcime. The only way he published this, unfortunately, were these this was a page size 8.5 by 11 map, and it shows a lot of mineral zonation through the caldera that implies a tremendous amount of work, a lot of X-ray diffraction or other mineralogical analysis, somehow identifying all these things. But unfortunately, this map is the sort of the sum of publication about it. Whatever was used to determine the mineralogy has not been published, and in fact, there was basically a refusal to publish the information, which is disappointing because modern work to a considerable extent has confirmed a lot of the mineralogy and other characteristics. It's been concentrated in the Thacker Pass area to the south and in an area in the north in the Oregon part of the caldera, where two companies have done work and sponsored some research by students. But the implication of the tremendous amount of data throughout the caldera, that has not been replicated at this point. Anyway, the modern work does confirm the general mineralogy, the lithium smectite, zeolites, albite, orthogenic case bar. And this is a very typical assemblage of a closed hydrologic system diagenesis. In talking about that, one of my colleagues, it's taken a while for diagenesis to catch on, let's say. One of my colleagues who had worked his life in porphyry copper deposits thought diagenesis was some sort of progressive mumbo jumbo, as I think what he called it. But it's generally now accepted, I think, with a little misunderstanding of what exactly diagenesis means, that these systems have all undergone this. The question, though, really is the higher grade lithium illite. It overprints the lithium smectite, therefore it's younger than the lithium smectite. It's only known in the southern Thacker Pass part of the caldera. A recent paper interprets that the lithium illite is hydrothermal, forming at greater than 230 degrees C. And specifically, it's related to caldera magmatism and faulting during resurgence. And there's some problems with that interpretation. A hydrothermal origin may be true, but the geology, the basic geology, is not consistent with that particular interpretation. And notably, there's many factors. The illite is supposed to be related to resurgence and to faulting during resurgence. Well, resurgence occurred quite early on, and the mineralization goes to quite a bit later than resurgence. It affects everything up to at least 15.7 million years, maybe younger than that. The faults that are cited, this is the Thacker Pass area, and you can see there are some faults, but there are faults like this throughout the caldera, and there's not an equivalent to Thacker Pass in these other areas. And the timing of these faults, they displace everything, including the intracaldera sediments. So the later activity of the faults long postdates resurgence. It is possible that the faults began with resurgence, although they could be just related to basin range extension. But we really don't know when they started, and there's no definitive evidence that to say they're concurrent with resurgence. So calling upon them to be conduits for hydrothermal fluids is it's not really established. It may be, but it's not really established. Additionally, the Lithium America's chief geologist, in talking with him about all these deposits here, he says that the grade of the deposits, the lithium illite, et cetera, shows no relationship to the fault. So there's just big uncertainties about how this might tie into resurgence. And something I am going to mention here, but I haven't mentioned yet, is that we've dated orthogenic potassium feldspar. And I guess I'm going to show this on a later slide. So I'll just say that we're going to say something more about the timing of mineralization in a minute. But I may also point out, people in your class may have been seeing some fairly pretty mineralization from porphyry or other deposits. This is a small pit in some high-grade lithium ore, and it has to be some of the ugliest material ever in terms of mining. I mean, basically it's just solidified mud, but it's got a lot of lithium in it, so it's got some value. Okay, one of the really big problems with the hydrothermal high temperature origin of lithium, of illite, is that there's abundant published evidence that illite can form at just basically room temperature. And that's particularly true of the East African Rift, which is geologically a lot like the extensional basins in Nevada and the other parts of the Western US. Now, here's the paper that says hydrothermal enrichment of lithium, 230 to 300 degrees C for the formation of illite. And in this East African basin, structural basin with a lot of rhyolitic glass input, they point out that here's this statement here: modern samples mostly contain illite, magnesium-rich smectite, and some kaolinite. Over here, a common example of such an alteration project is low-temperature orthogenic illite. Here's a paper from, and that's going on at the present day. Here's a paper from the Eocene and the Oligocene. Present work indicate that smectite can be transformed into illite, smectite, and illite at surface temperatures by wetting and drying. So there's abundant literature that says that illite does not require high temperatures. It doesn't say one way or another about the McDermott illite, but it certainly doesn't require high temperature. Okay, a little bit of data on
Looks like you got a question. Looks like you got a question.
Sure.
Yeah, Chris, has anybody done oxygen hydrogen isotopes on the illite?
There has been some, and I'll mention briefly a little bit.
Okay.
Yeah. Okay, we've done a lot of X-ray diffraction work on it. This plot here is from a publication a few years ago. We're looking at the despacing versus lithium content. These are bulk samples. And what you see is, and the despacing illite, smectite, transitional, and smectite. And you can see that the smectite and transitional, they're limited to about 4,000 ppm. Now, these are bulk samples. They're not pure lithium smectite, but that's an indication of the that smectite has lower lithium concentrations than the illite, where we have up to about 7,500 ppm. And in fact, we've got data up to about 9,000 ppm for the illite dominated sediments. And this is basically what everybody's found, that the illite contains significantly more lithium than does the smectite. Yeah, here we go. In addition to dating the host sediments, also dated an orthogenic potassium feldspar in the illite zone, and this comes out, it's a very good date, 14.87 million years, and it's in the illite zone, so it's interbedded with illite. It doesn't say for certain that the illite formed at the same time, but that is certainly a suggestion and indicates that the illite may be quite late. And if that's true, then the obvious question is for what would be the heat source to generate hydrothermal illite long after any of the magmatism has ceased. There's some work by others dating what they call snowball carbonate, dating by uranium lead, and they got a pretty imprecise 14.3 million years, plus or minus a million years. And they said this was a minimum age of illite mineralization, and said this was sort of consistent with our orthogenic date, orthogenic case bar date. At this point, I'd say that the timing of illite formation is not perfectly constrained. It certainly seems to be late and long post-date any caldera magmatism, which begs the question of what would be the hydrothermal heat source for any high temperature illite. We're attempting to date the illite, as you're going to see in a second. It has a fair amount of potassium in it, so it should be amenable to argon 4039 dating, but it has not been easy, and it's not been successful so far, but we're going to keep trying. Okay, some SEM images of the smectite images and compositions. SEM cannot analyze for lithium, it's too light, so that's not included in these analyses here. And these analyses are in weight percent of the element. And what you can see is that the smectite, first of all, you can see that it's extremely fine grained. Here's 25 microns, micrometers here. And the smectite and the illite are down in the sort of 1 micron range. The smectite has pretty high magnesium, which is interesting because most clays are aluminum rich and these are not. And that seems to be generally true for most of the lithium smectite deposits, not just Nevada. Also high fluorine, a moderate amount of potassium. Now the illite, equally fine grained. You can see these tiny little things. It's hard to even distinguish individual crystals in there, but they're down in the micron range. And they have lower magnesium, which is consistent with the sort of crystal chemistry of illite versus smectite. Higher fluorine, higher potassium, and some aluminum. And I don't know in this case if the aluminum is definitely in the crystal lattice or is a contaminant of some other mineral in there, but there does seem to be a consistent difference. We are trying to date the illite, but as I say, it's been unsuccessful so far. Now, obvious question, what is the lithium source? And in our 2020 publication, we did a very rough mass balance where we looked at the amount of lithium in the glass in the tufaceous sediments, which because they all have dissolved and everything in them has gone into solution, is one obvious source. And our conclusion is that that source is probably insufficient to provide all the lithium in the caldera today in mineralized deposits. And basically what we did is just calculate the area, thickness, volume, therefore, of rhyolitic tufaceous sediments that underwent diagenesis. And assuming that they started out with 100 ppm lithium, they could have contributed 22 to about 40 million tons of lithium into the caldera. And then we compared that, and mind you, there's a bunch of assumptions that go into it, and I'm going to show that at least one of the assumptions made here is wrong. We then compared that with the deposits, and Lithium Americas, the company that has Thacker Pass, has actually published some data, and they have in their deposit, which incorporates just a small area of the caldera, they have about 3 million metric tons. Jindali, the Australian company that has the deposit in the northern part of the caldera, they have about 4 million metric tons there. And these are deposits of just small areas. And so if we extrapolate them around the caldera, and there's lithium mineralization throughout the caldera, lithium smectite anyway, our best estimate is something around 130 million tons of lithium in the mineralized deposits there. This is a very rough calculation. It is based upon several assumptions, but at least at the time we published this, it really looked like the tufaceous sediments could not provide all the lithium that is in the mineralized area. Plus, if the tufaceous sediments alone were the source, then there ought to be large volumes of the tufaceous sediments that are very depleted in lithium to be concentrated in the deposits. And one thing that shows that even I can make mistakes, recent drilling just in the last year or so by Lithium Americas in the eastern part, and I'm pointing over here in the southern part of the caldera, intersected a lot more tufaceous sediment, up to about 400 meters of tufaceous sediment. So there's substantially more rhyolitic tufaceous sediment out there than we realized at the time, which was based upon outcrop and the drilling that existed at the time. So that would increase the amount of lithium potentially available. Further calculation, though, still suggests that the tufaceous sediment alone is insufficient to provide all the lithium that we see in deposits. So what's the other source? And a special thing about the McDermott caldera is it has a lot of hydrothermal non-lithium mineralization in it. Has a lot of hydrothermal mercury, uranium, gold, and silver over, it's supposed to be somewhere located over there, and it doesn't seem to be there. Did I miss something? No. And it has an unusual type of deposit, uranium zirconium mineralization. And this is obviously uranium, but also enriched in zirconium up to around 40,000 parts per million, or 4%. And the uranium occurs particularly as a lot of uranium-rich zircon. And there's two geologic settings to this uranium zirconium mineralization. One, and we're looking at the western caldera wall here. One is along the caldera ring fracture through here. And the most prominent deposit, the Moonlight Mine, I've dated adularia from there. It comes out at 16.35 million years, or just barely younger than the caldera tuff. The mineralization is along the ring fracture zone, so we know it's post-collapse, but it reasonably is interpreted to be part of a hydrothermal system generated by the McDermott tuff magmatic heat source. That's one setting. Another setting is right at the top of the intracaldera tuff, base of the intracaldera sedimentary, the clay, lithium clay bearing section. And it's lower grade than the things along the ring fracture, but it's geochemically very similar and has some similar mineralogy. And so it's right at the contact between the intracaldera tuff and the overlying intracaldera sedimentary sequence. And so it looks like it's probably related to degassing of the intracaldera tuff. And I'll explain that a bit more in a second. This is just a geochemical comparison of the uranium zirconium mineralization versus the lithium mineralization. None of the hydrothermal deposits in the McDermott caldera are enriched in lithium. They're all 100 ppm and less. And what we've done here is take a couple different examples of the ring fracture uranium zirconium mineralization, these two things here, and the tough sediment contact uranium zirconium, and then also a variety of lithium mineralized samples, and plotted them as a ratio of the average lithium concentration in the sample to average lithium mineralization. Now, what that means, of course, is we're basically plotting these samples against themselves. So they're going to wind up all along close to the 1-to-1 line, although the illite is distinctly more enriched in a bunch of the elements, including lithium. In contrast, though, the uranium zirconium mineralization is very, very different. Obviously, very enriched in uranium and zirconium here, these two elements, but a variety of other elements, and very depleted in lithium, cesium, rubidium, fluorine, all of which are highly enriched in the lithium clay deposits. And so this hydrothermal system absolutely did not directly generate the lithium clay deposits, but they could have contributed to it. And I'll explain that in a second, after first digressing and mentioning this Nevada North deposit over here, far out. It's sort of isolated, at least as far as we know, by itself in northeastern Nevada. And this is an example where there's very little geologic work that's been done. The company reports some pretty good lithium grades, and that it includes lithium illite, which makes it pretty significant. The only geologic map, this figure on the left here, is our county report at a scale of 1 to 250,000, very non-detailed. The white box here is the area that the company has their prospects in. They're definitely in rhyolitic tufaceous sediments that have undergone diagenesis in a structural basin here. But that's the sum of really what we know about, other than what's been published in their press releases. And I bring that up because we're now going to look at some geochemical data from our Big Four: Thacker Pass, Nevada North, Rhyolite Ridge, the lithium boron deposit, and Tonopah. And what we're going to see is a series of plots where we plot lithium on the lower scale against some other element, in this case magnesium, on the vertical scale. And note that the scales are different. Here at Thacker Pass, 0 to 9,000 ppm, Tonopah, 0 to 2,000 ppm. And there's a tremendous difference in data availability. Lithium Americas has been very generous with their data, so we have a tremendous amount of data for Thacker Pass. Nevada North simply published these diagrams in some of their press releases. Tonopah also have access to a lot of data. Rhyolite Ridge, very, very little data. All we have really is some analyses from a master's thesis done at the University of Nevada, Reno, and those focus just on highly mineralized samples, so a very restricted range and a very small number of analyses. But you can see there's some interesting trends here. Thacker Pass is our best example, and you can see there's a high lithium, low magnesium trend. And as you remember, the illite has higher lithium, lower magnesium than the smectite. And so this is the illite trend here. This trend here matches smectite, has a maximum value around 4,000 ppm. That's what we saw in our X-ray diffraction data previously. However, there's also a trend here, which is a curiosity what this is it seems to be a higher magnesium, somewhat lower lithium, but still significant lithium trend. And I don't know for certain what that represents. Now, because we have these things at different scales, what I did is take the Tonopah data here and convert them to the same scale as Thacker Pass. And so now we have that data published here. And curiously, although all that's been recognized there is lithium smectite, there do seem to be these multiple trends that correlate with illite, smectite, and whatever this unknown is here. And at this point, I could speculate about what it means, but I really don't know. Note for Nevada North, and that's our next plot will show that.
So
It
can I
goes
ask a
up
question, Chris?
Sure.
So it looks like you want illite if you're looking for lithium.
Yeah.
What is it about illite that accepts more lithium than smectite? Is it a crystallographic control or what?
It is crystallographic. It's, there's a bunch of sites in a clay mineral structure, and I'm not any expert. There's interlayer sites, there's actual within layer sites, and illite can just incorporate more lithium. An important difference, in addition to the higher lithium concentration in illite, smectite is a swelling clay, illite is not. And processing always uses water. And the smectite, if you can picture driving across a Texas farm field in clay in the middle of a rainstorm and getting stuck in mud, that's sort of the situation with lithium smectite. Let's see. Okay, we now have Nevada North plotted here, and you can see it largely follows the illite with a little bit of a smectite trend too, but there's definitely smectite there at Nevada North. Okay, several other elements. Here's rubidium, which is geochemically like lithium and definitely follows it. It has the same sort of trends. For Thacker Pass, this would be the illite trend going to the higher lithium concentrations, higher rubidium concentrations. This would be the smectite trend, lower lithium. And there's also this oddball thing of higher rubidium, but not real high lithium. And we see that to some extent at Nevada North. We just don't really have enough data for Rhyolite Ridge other than to say that 800 ppm rubidium is pretty high for any average rock. Tonopah does not really show any really significant relationship to rubidium and not terribly enriched. But the incorporation of rubidium in the various clays, it's definitely, it's consistent with the clay mineralogy and composition. They can incorporate rubidium and notably magnesium, fluorine, and cesium, all of which nicely correlate with lithium and illustrate the different smectite and illite trends. Okay, arsenic is also enriched in the lithium deposits, but it's not in the clay minerals.
Another question for you, Chris.
Yeah.
Another question for you. So sodium is the alkali metal that's most like lithium. What does sodium show?
It goes away. It does not show up in the.
Okay, so
yeah.
it's basically all gone. It's negligible sodium in these.
And that's it actually gets into. There's so many aspects that could be discussed here. We could go on for days, and we're not going to. There should be a lot of sodium there, but it just seems to have gone away. Where did it go? And I don't have a good answer for that. Arsenic, the lithium deposits are definitely enriched in arsenic. You can see at Thacker Pass, you get up to more than 1,400 ppm. Nevada North, 300, not terribly high, but that's significant. Tonopah up to nearly 600 ppm. not all that enriched in Rhyolite Ridge, but 200 ppm is definitely arsenic enrichment. However, there's no correlation between the arsenic and the lithium, which says that the arsenic is enriched by the process that generated the lithium mineralization, but it's not incorporated in the lithium clays. It's probably gone into pyrite, arsenopyrite, other sulfide minerals. And just a quick comment about boron. Rhyolite Ridge, of course, has very high boron. It's a lithium boron deposit. And the other places don't have boron data except for Nevada North. And maximum boron concentrations there are only about 600 ppm, much, much less than Rhyolite Ridge. But you can see there's a correlation between increasing lithium and increasing boron. So it looks like the mineralization process enriches boron in a combination of dissolution of the source material and evaporation. But the starting material is critical. The starting material at Rhyolite Ridge probably had a lot of boron. There's possibilities of why that is, whereas Nevada North and other places did not. And so it might be mildly enriched, but not to the extent that we'd have lithium boron deposits. Okay. I mentioned that the Yellowstone hotspot doesn't have, the calderas mostly don't have a lot of hydrothermal systems in them, McDermott being a big exception, and an obvious exception is Yellowstone, because as we well know, Yellowstone has a lot of geothermal, hydrothermal activity, geysers, mud pots, etc. And the USGS and others have done a lot of research on the systems at Yellowstone. And this is a USGS professional paper here that looked at the geochemistry of Yellowstone Lake. This is the youngest Yellowstone caldera, 600,000 years ago. Magmatism has continued up nearly to the present day. Yellowstone Lake is partly an intercaldera lake, partly outside the caldera. Unlike the lake at McDermott and other places, it was not a closed basin. Yellowstone Lake drains out to the Yellowstone River, to the Missouri River, and ultimately to the Gulf of Mexico. But it does have a lot of hydrothermal vents underneath the lake. And in this study, the USGS looked at inflow to the lake. All these small arrows are creeks draining into the lake, and they sampled them through time to look at the input to the lake. And then they looked at the composition of outflow, the Yellowstone River draining out here. And what they did is compare the inflow composition to the outflow composition. And if the inflow and outflow were exactly the same, they would plot on this diagram. And this is a ratio of the inflow concentration to the outflow concentration. And it's in log units. So 0 is a ratio of 1, so that would be no change. -1 is that's a log unit, -10. So 10 here and 100 here. And what we can see is that the outflow, the Yellowstone River, has something like 50 times as much lithium as the inflow. And the outflow is also enriched in molybdenum, antimony, cesium, arsenic, somewhat in rubidium, somewhat in sodium. And it's very depleted relative to a bunch of other elements. And what this is saying is that if Yellowstone Lake were a closed basin, it would be accumulating lithium. It would be generating lithium deposits. It's not a closed basin. The lithium just flows out with the outflow, and so there's no lithium deposits forming there. And question? Okay, I think I'll skip this, save a little time here, and just go to this model and then what can be done to test some ideas. This is my hypothesis for the origin of the lithium deposits at McDermott. The rhyolitic tuffation sediments are definitely a source, but we need an additional source. And I'm saying that hydrothermal fluids did come into the caldera and into the caldera lake, but early on. And they did that by, here we have the, where'd my cursor go? There we go. The hydrothermal uranium zirconium deposits here along the ring fracture system, and then hydrothermal, some sort of deposits along the sediment McDermott Tuff interface right here. The intracaldera McDermott Tuff, when first erupted, would be a mass of rhyolitic glass. As it cools, it devitrifies, and any volatiles, including particularly lithium, trapped in that would be spit off, so to speak, and it would discharge right along this contact, and that's where we see this uranium zirconium mineralization, and it would be just right in the bottom of the sedimentary sequence, because the devitrification of the intracaldera tuff would end after a short time, and so it would only contribute there. But all this discharge is going into groundwater or potentially lake water in the intracaldera system. And once it's into that groundwater, lake water, it's trapped there. So it's available for later incorporation into other deposits. And what I'm suggesting is that the uranium zirconium hydrothermal fluids probably also had lithium, cesium, rubidium, et cetera, in them. The relatively, in this sense, immobile elements of uranium and zirconium precipitated to make those deposits, but the more mobile elements, lithium, rubidium, cesium, fluorine, they are easily soluble in cold saline water, and so they just continued into the intracaldera hydrologic system. They're trapped there, but they'll be available to make later lithium deposits. And there's some publications here that would support the concept, and particularly I point out that the Yellowstone paper, looking at their data, they show that the hydrothermal vents just between Yellowstone, but beneath Yellowstone Lake, are discharging some 530 tons of lithium per year into the lake. And that's just per year, and that's just a small part of the Yellowstone hydrothermal system. So if Yellowstone Lake were a closed basin, we'd be generating lithium deposits there. Now, this is a hypothesis, and there's some obvious things to test it, and I'll get to that. One immediate question is, this mechanism would seem to apply throughout the McDermott caldera. So what is special about Thacker Pass? And I don't have a good answer for that at this point. But here are some things to test this idea out. I've mentioned the 4039 dating of illite to really nail down its timing. You saw that it's ultra fine grained. It's been very difficult. We've been unsuccessful so far, but I'm working with some very good clay mineral people in dating, and we're going to try to figure that out. Another thing is to determine the actual temperature of illite formation. And there's a variety of mechanisms to do, including stable isotopes, which I'll mention one example of what's been done there. But one commonly used method to determine the temperature of sediments is vitrinite reflectance. Vitrinite is just organic material, commonly from plants, and it's used extensively in the oil business. Its sort of evolution is it becomes, has a higher reflectance the higher temperature it's encountered, and it's pretty well calibrated. I'm collaborating with a couple geologists with USGS in Reston, Virginia. They've been going very slowly. They've had the samples for a year, and I just got from them recently that some preliminary, the vitrinite shows low maturity, and that's not a good temperature number, but it says the illitic sediments are low maturity. It does qualitatively say that they're probably pretty low temperature. Another method is illite crystallinity, and this looks at the shape of the illite peak on X-ray diffraction. And there's a plot by a guy named Kubler, and he's the namesake of the Kubler index, which is the illite crystallinity index. And basically it says that broad illite peaks like this are consistent with low temperature. Crystallization at higher temperature, the peaks become narrower, sharper, and at high temperature, they're very narrow, sharp. Now, there's some sort of discussion about how good a measure this illite crystallinity is. Some people really disparage it. Some people, it does get used extensively, so some people obviously liked it. It requires certain X-ray diffraction process techniques that I don't believe really have been done on any illite samples anywhere. The X-ray diffraction we did, and this is a plot of some of our X-ray diffraction on the vertical plot here. This is a smectite peak. This is an illite peak. And we didn't do it the exact way that would be required to do the illite crystallinity. Nevertheless, what we see are very broad peaks. And this is another recent publication, again, on Thacker Pass. And they looked at a section here where this is a smectite peak, and then it's a transition downward into illite. And you can see all of these are very broad peaks. So qualitatively, it certainly doesn't suggest that illite is high temperature, but it's a little equivalent as to what exactly it means. Another temperature, and this is from two different deposits. There's a major lithium boron deposit in Serbia, and this mineral here is yadarite, named from Yadar, Serbia, where it occurs, and maybe the only known occurrence. And they looked at a combination of things, including mineral equilibria and oxygen isotopes. And what they find is a range from about 50 degrees C to maybe about 95 degrees C, which I think is pretty reasonable. And I'll comment on this other one first. Here's one from, including a co-author here in the audience, I think today, a deposit in Barstow, California. This one only contains lithium smectite, as far as I know, and they give formation temperature ranges. This is based upon oxygen isotope and I think also the clumped isotope, carbonate isotopes, and they mentioned temperatures of 17 to 51 degrees C. And I think these are pretty reasonable temperatures. If we back up, I plotted here sort of a best interpretation of diagenesis zones going into a transitional zone into low-grade metamorphism, and sort of interpreted temperatures. And different people sort of argue about what these temperatures are, but we're seeing low temperatures for diagenesis, mostly less than 100 degrees C, but in some cases in higher grades of diagenesis, somewhat higher. Whereas when you're getting up into, and notice the tighter illite peak, 200 and even 300 degrees C, once we get into low-grade metamorphism. I think this temperatures in the somewhat less than 50 degrees, or maybe 50 degrees up to even 90 degrees C, they're consistent with diagenesis. At least diagenesis generates that kinds of temperatures. Hydrothermal systems, you're not really seeing much evidence for anything at 200 degrees C or higher. So I'm sort of doubtful about that. But that's an example of where ongoing research needs to be done. One other thing, I hypothesized that these hydrothermal fluids that generated the uranium zirconium mineralization also generated, had lithium and other things in them. And a way to test that out is to look at fluid inclusions in the uranium, zirconium, and other high thermal mineralization and look at their compositions. Do they contain lithium, significant amounts of lithium, cesium, et cetera? If they do, then that would be consistent. If they don't, then that would say that this mechanism doesn't work. Anyway, that's some things I'm working on. There's a lot of other things to do, just a tremendous amount of opportunity for research on the origin of these deposits, and just exciting time to work on lithium deposits. So thank you very much.
Yeah.
And I'm sure I've said something controversial or unclear, so I welcome any questions.
So I've got one real quick. What is the relationship between lithium mineralization and the 706 line?
I think.
So just to remind the class, the 706 line is where the initial strontium 87-86 ratio of 706 is higher to the east, lower to the west. It's taken to be the edge of the craton before deformation. So it's kind of old crust margin. Is there any relationship to that?
Well, this figure here, this line here is the 706 line as interpreted by some. There are different 706 lines. But definitely craton here to the east and accreted Paleozoic basaltic terrain to the west. McDermott is off into the accreted terrain, but it definitely has a cratonic component to it. A student at Washington State University did a PhD on McDermott, looking at petrogenesis, and the fundamental magmatism is this Columbia River basalt type magmatism. That basaltic material has interacted with different crusts. Some of it has gone to the McDermott magma caldera magma system, which is a peralkaline system with very little indication of input of crust, of continental crust to it. But there are also these metaluminous biotite bearing rhyolites that do have a significant indication of continental crust input. And continental crust is commonly called upon to be actually the source, ultimate source of lithium trapped in like biotite in old continental crust. If so, that might suggest that the metaluminous biotite rhyolites at McDermott would be more favorable than the actual McDermott magma system itself. But that's another topic for further research.
Other questions?
Yeah, Chris, do you do the argon in-house, or where do you get that done?
I do it all at New Mexico Bureau, the New Mexico Tech and the New Mexico Bureau, the New Mexico State Geological Survey.
Matt Heisler.
Yeah, they have an exceptional argon 4039 lab, and I just fortuitously met the guy who built it, Bill McIntosh, long ago. And he said he was setting up a lab and I ought to come there when he got the lab set up. And I have. I first went there in 1993 and I've been going back every year since. And for any 4039 dating anyone's interested in, I highly recommend the place.
Yeah, I've used it before. Yeah.
Any questions from the students? So
this is a little bit off topic, but what do you think of kind of some of the new approaches to either like lithium mining or other kind of mining, like re-going over the tailings in some of these mines?
Different kinds of lithium mining?
Sorry, no, I guess this isn't exactly on topic, but just the idea of going through like mining tailings to to capture stuff that hadn't previously been captured, I guess specifically for lithium.
old mine tailings and recovery. Yeah. For a lot of elements, that's extremely promising. One of the highly cited things is rhenium in porphyry copper deposits. Porphyry copper has a significant amount of rhenium. Has generally not been recovered, but it could be. And I think I heard that the Bingham Canyon giant porphyry copper deposit in Utah they've set up some circuit to recover either rhenium or another critical metal, and that's forecast to solve the US's deficiency in whatever the element is. I think recovery from old tailings is very, very promising. There's just a lot of elements that at the time, somebody was mining for gold or for copper or silver or whatever, and there was these other elements there, but they weren't interested. There wasn't a market for them, so they just flushed on out to the tailings pond or the rock waste pile, and so those could be relooked at. That's definitely worthwhile.
But in general, though, the older the tailings, the more attractive they are to reprocess. And I guess tailings associated with lithium mining wouldn't be very old.
No, I mean, there really isn't any, I back that up. There has been lithium mining in the US. A lot of pegmatites in North Carolina were mined for lithium because they had the spodumene or lepidolite long ago, and there might be potential for reprocessing there. I just don't know the situation well enough. But yeah, old deposits. This was actually done. Silver mining commonly recovered only about 50% of the silver that was actually mined. And this was recognized a long time ago. So a bunch of people in the 1980s, went back to old silver mines, reprocessed the tailings, and recovered a whole lot more silver. Our technology for everything has gotten better over the years.
Is this the Kings Mountain LPT pegmatite in North Carolina? Is that what you're
What's that?
referring to?
The Kings Mountain?
Is that the North Carolina mine?
Yeah.
That sounds
and I don't know the history of that very well, but I'm pretty sure that was mined significantly. It was a major source of lithium in the United States for a long time. It shut down at some point and is being considered for starting back up. There is some local opposition. People, for not surprisingly, don't want to see a mine in their backyard. And I don't know what's going to come of that, but there is significant lithium resource there.
Okay. And then it looks like it was also had tin and tantalum.
I mentioned the Australian pegmatite deposit, Greenbushes, which is the leading producer of lithium at the moment. That mine started, I believe, in the very late 1800s for tin. Somebody found a boulder of some sort of tin mineral, and that was mined for tin for a long, long time. These pegmatites have a mix of things. I was in England, the United Kingdom. They're looking at some of the Cornwall tin deposits. Cornwall was famous for mining tin. And those deposits apparently do have a significant amount of lithium, some other minor elements, and they are being investigated as, a source of lithium, probably reprocessing tailings now.
I'm not sure. Why would you expect to find tin and lithium together? I'm not sure if I understand that mechanism.
They don't occur together in the lithium clay deposits. They do occur together in these pegmatites, and I'm not sure exactly the full geochemistry. I think both elements are not incorporated into normal rock forming minerals. So as the magma crystallizes, they're excluded and they're concentrated in the residual magma, and that includes lithium, tin, and boron. And pegmatites also contain tourmaline, which is a boron mineral. And so these elements, I think what they have in common is that they are concentrated in residual magmatic liquid and ultimately available for pegmatites. There's obviously a lot more to what's going on than that simple explanation, though.
Yeah, they're S-type granites are usually associated with tin, also A-types, not your I-types. So
yeah,
this is kind of a back arc magmatic setting. If you characterize McDermott, I imagine you'd call it an A-type, but I'm not sure.
yes,
So,
yeah.
It seems like if you want to find lithium in these kinds of deposits, you're looking for a caldera with a closed basin, right?
Yes, but interesting. McDermott is a middle Miocene caldera, and there's all these calderas related to the hotspot. On this figure here, you can see several smaller calderas sort of scattered around the McDermott area. This one here, which is not even definitely a caldera, but certainly looks like a caldera, just hasn't been studied, it has a little bit of lithium enrichment. None of the others do. And they've been looked at enough to suggest they really don't have any lithium. So why that is different, that's another topic really for a major research effort. What is special about McDermott that just either didn't happen or only happened on a very small scale in these other places? And I could arm wave, but that's about all I could do at this point.
So just to follow up on my idea, Mono Lake seems like an actual caldera that's got an internal drainage. Has that been looked at for lithium mineralization process?
It
Does
actually
Mono
isn't
Lake
a
have drainage?
What's that?
Oh, sorry, I didn't think Mono Lake had drainage. I thought that's why it.
Right, it's internal.
Yeah.
It's a terminal lake, as I understand it.
Oh,
Is that
yes,
yeah.
that's correct. Yeah, it's a
so
terminal lake. I don't think it's a caldera. I think it's more a structural setting.
interesting?
But and I know people have worked extensively on monolake chemistry. I don't know what it shows in the way of lithium, but I think it is somewhat enriched in lithium. I know some of the other terminal lakes in eastern Nevada, eastern California, southwestern Nevada also have lithium concentrations. That's about as much as I can say for it without looking up some published data.
Yeah.
If
Cool.
anybody else can comment. One thing about calderas, you don't see it on this map, but Nevada was a part of what's called the Ignimbrite flare-up that occurred throughout Western North America, from Oregon, Idaho, down through Nevada, Colorado, New Mexico, Texas, and into the Sierra Madre Occidental of Mexico. Lots of calderas. The examination of these mid-Cenozoic calderas, none of them seem to have lithium either. They had some of the same ingredients of a closed caldera basin and rhyolitic tufaceous sediments. I don't know that any that have actually undergone closed hydrologic system diagenesis. But I also don't know of much investigation of that topic. But so far, none of them have shown any lithium enrichment.
Cool.
So calderas are good, but they're not enough on their own.
One non-related question. think in the introduction, either Dr. Stern or you mentioned Nevada, you said lithium, gold, and silver. Is there anything going on in silver in Nevada?
Oh, yeah. Yeah, there's a lot of silver mining. Many of you may know that the prices of gold and silver have just skyrocketed. Silver was down in the upper 20s and is now, it was up as high as $50 per ounce a while ago, and it's in something in the $40 range.
57 today.
How much?
57.
57.
Wow.
Okay.
Wow.
And Nevada is officially the silver state. It had a lot of silver mining. Carlin type deposits have very little silver accompanying the gold, but many of the other deposits in Nevada have a lot of silver, more silver than gold. Gold, by being worth a lot more, is the major commodity, but several deposits produce a lot of silver, and some are primarily silver producers. So yeah, a lot of interest in silver also.
Thank you.
Any other questions before we let Chris go?
I got one last one. Those fluoride contents of the illite seems really high,
Yeah, that's
like really high.
they are.
Yeah, 15 weight percent. That's
Yeah, and here's the smectite, which actually has a little lower. Here's the illite.
yeah, that's
Yeah,
still
15%.
Yeah.
It is consistent with the crystal chemistry. I mean, clay minerals are gigantic garbage cans.
They are.
There's so many different kinds, and this taniolite, for example, is sort of the best match for the taniolite is the lithium illite. It is the best match so far for the lithium illite that's been found at Thacker Pass. But I suspect that other mineralogical research in the McDermott caldera elsewhere is turning up a lot of minerals that most geologists have never heard of. Labuntzevite, I'm sure just rolls off your tongue. It is a potassium thallium something or other. I'd never heard of, and somebody just found it, and it took them a long time to figure out what it was. The point is that there's some surprising mineralogy, and I think that's going to apply also to the clay mineralogy, in that the lithium clay minerals may be close to some recognized compositions, mineral structures, but are going to be a little bit different.
Cool, thanks.
Any last going once, going twice? Well, thanks very much, Chris. We really appreciate it.
Thanks, Chris.
Okay.
We learned a lot.
Thank you.
Not just about lithium, but also about Nevada, which is obviously a hot spot for mining and job opportunities for students. And by the way, Chris has been very helpful in identifying job opportunities in Nevada via LinkedIn. And Chris, you said if you join the Nevada Geologic Society, you get all the notices free.
Yeah.
What does it cost for a student to join?
Well, I know for me it's $50 per year, and for students it's a lot less.
Yeah. So if the prospect of a entry-level job in Nevada mining interests you, I encourage you.
Yeah.
Beautiful
Thanks.
place.
Yeah. Thanks again, Chris.
Okay.
Thanks, Chris. Yeah.
All right, guys. We'll see you next week for the presentations.